So, dear students, welcome to the lecture number 2 of digital control systems. In this particular lecture, we will understand the various problems which are uh, associated with the digital control and the implementation of digital control to get the desired output of any plant. So, now when we talk about the problems which are associated with the implementation of digital control are the sampling and the quantization. Now, this can be easily understood from the block diagram as shown here. This block diagram explains the digitization of or discretization of any continuous time signal. So the overall process can be understood from this small block diagram. As you can see here, we have a computer which acts as a digital controller. So this computer understands the digital signals and it gives us the digital signals as output. But our real world that does not understand the digital values. The real time process or real time plant only understands the information in analog form. So we need to provide this information to the real time plant or real time world in analog form. So the analog signal which is available to us is converted using A to D converter. So this is our analog to digital converter, and this is digital to analog converter. So the analog signal is converted, or we can say the continuous time signal. So this is a continuous time signal is converted to discrete time signals by using A to D converter, and computer will process this signal and gives us some discrete output or digital output which is converted back to analog signal uh, through D to A converter, that is digital to analog converter. Now, this is how it works basically. This is how the digital control works. So only this particular part is the digital means this is processing the information in digital manner. So most of the processes which we know are they are continuous time processes, whether it is the temperature control or pressure control or level control, flow control, speed control. So most of the processes in real time are the continuous time processes or analog processes. So we are dealing with the analog environment as I already mentioned. Now, to deal with this particular analog environment and the digital computer, so to deal between these two totally different systems, analog system and digital system, we need some interface. So those interfaces are provided by these two types of converters, A to D converter and D to A converter, so that the relevant information can be processed in convenient way and effective signal are the sampling and quantization. So let us see what are these effects basically. So the first is the sampling effect. Now sampling is basically the conversion of any analog signal. If you have an analog signal with you, let us say this is some signal which is xt, it is a continuous time signal. So when you collect the data of this analog signal at some specific uniform interval of time, so this particular signal will be converted into the sampled signal, and we have the samples instead of the time values. So we have all these samples with us like this. So that means instead of having the continuous data, we only have some finite samples, and the process of converting the continuous data into the sample data is known as sampling. But sampling is not that easy as it is being described. So we need to take care of certain things while sampling any particular data. And the first thing is the sampling rate, at which rate we will sample the data. That is very important. Now why it is important? Because it is important because now for example you have uh, a continuous time data xt, and it is something like this for example, and you have sampled this data. Now, when you have sampled this data and you have done the uniform sampling means sampling or getting the samples at equal interval of time. So the time period of two successive samples will be same, right? So when you sample this, you are getting some sample data. So instead of t, now we have k. Instead of xt, now we have xk. Now we have samples basically. So we have zero sample, then here we have, then here, then here, then here, and like this. So one thing you must have noticed here, that when you have sampled the data, the information between these two successive intervals is lost. Loss of information, right? So this is one thing, and because your computer does not understand analog quantity, so it is uh, we are compelled to convert the given continuous data into the sample data so that we can easily convert that information into digital equivalent. Now, losing information is inevitable in this particular process. We cannot do anything with this. But yes, what we can do is we can take care of the sampling rate, the rate at which we sample the data. That means the frequency is to be taken care of, right? So the frequency of the sampling frequency, basically it is very important. Why it is important? Because you can see from this diagram. So if we sample the data with the correct sampling frequency is the number of samples per unit time, the number of samples captured per unit time, and that number of samples captured per unit time should be uniform throughout the process. So the either you can say that the sampling rate is taken care of or the sampling frequency is taken care of. It is one and the same thing. These two are not different. So the sampling frequency which we need, or the choice of sampling frequency, basically is defined by the sampling theorem, which states that any continuous time signal which is present to us need to be sampled. That means the number of samples that you need for any continuous time signal per unit time should be greater than equal to the twice of the maximum frequency component that is present in that particular analog signal. That means the analog signal which we are going to sample must be having the maximum or highest frequency value, twice of that highest frequency value, greater than that or equal to that shall be the sampling frequency of that particular analog signal. Only then you would be able to get the perfect sampling. Otherwise, if you increase the sampling beyond, um, even if it is, the sampling frequency is very very high than the maximum or twice of the maximum frequency, in that case you will have samples wherein the frequency representation would be having some gaps. So here you don't have any frequency information, right? If you sample the given analog signal with less than twice of the maximum frequency component, so you would be having the overlapping, which we call as aliasing. So aliasing effect is seen here. So it is only when you have equal to, then we get the perfect sampling, right? Now this sampling theorem has certain limitations. So the sampling theorem was uh, described for or used for choosing the correct sampling frequency. Problems associated with this sampling theorem when we need to implement this to the practical control system. The first is that the real-time signals which we have are not band limited. Sampling theorem is totally meant for the signals which have some bandwidth, basically, because you can see in this equation here omega m. So omega m is nothing but the bandwidth of the analog signal or the signal which is to be sampled. Now generally the real time signals which we capture are not the band limited signals. That means they do not have a specific bandwidth, right? So this is one issue which is related to the real time signals. Real time signals like your temperature, pressure, flow, etc. That means real time signals from the process industries, right? The second issue is that we need to have the ideal low pass filter in this case. That means if you are measuring the temperature, pressure or something like this, so we need to have the anti-aliasing filter. So anti-aliasing filter is nothing but the low pass filter, so that the high frequency noise, high frequency components which are present in the real signals, useful signals, can be filtered out. So the ideal low pass filter is needed for the distortion less reconstruction of the continuous time signals from its samples. Now why it is important? Because when you have sampled the signal, you have lost certain information. Now you have processed that signal through computer will give you some digital output, but you will not understand that digital output, you will only understand the analog output. So when you will convert that digital into analog by using D to A converter, so in that case you need to reconstruct the signal. So the perfect reconstruction can only be possible when we follow the sampling theorem. But since sampling theorem we are applying to the real time signals which are not band limited, which do not have a specific bandwidth, right, which may have a lot of noise components present in them, So it is quite difficult to have the perfect reconstruction of the signal. So these two issues are always related to the the uh, the conversion, or related to the implementation of the digital control, because without using the digital signal we cannot expect the digital control of any uh, process. Okay. So the process of sampling means there are two things. One is we have the analog signal. We have the analog signal, for example, let us say sine wave. We sample it, we convert this into some sequence like this: k, xk, t, xt, and then we process it. We get some digital output. Then we take D to A converter. Then we need to have the same signal. So, but it is not practically easy to get the same reconstruction of the signal. So we may get something like this, a continuous signal like this. We may get a square wave, which is a continuous signal, but not exactly the sine wave. So these are the issues which are related to the conversion, which are related to the digital control, right? Now, this sampling and reconstruction process, what actually happens here, when we sample a signal, we convert it to digital form, so we quantize the signal. So quantization means we round off the value, the sampled value. Similarly, when we convert the digital back into the analog, even then also sampling and hold is done. So quantization is done at that point of time also. So now what happens? The overall performance of the computer or the controller is degraded because of this, because this is a complicated process, complicated uh, approach basically, and it will finally degrade the performance of the system. So for example, if we convert a continuous time signal into a digital control system, so if we do not change the system parameters, so it may affect the stability of the system or stability margin of the system. Stability margin, I hope you know, means the gain margin and phase margin of the given system. So we need to do something to the process, to the conversion process or approach, so that we can get the efficient or effective control of the processes. Now, these ill effects means the sampling, the signals are not band limited, signals do not have the perfect bandwidth, uh, low pass filter is required, the exact reconstruction of the continuous time signal is not easy. So all these ill effect can be reduced, but they cannot be eliminated completely. We cannot eliminate these things. They will exist into the system. We can reduce them. How can we reduce them? If we increase the sampling, if we do the sampling of the continuous time signal at a great rate. That is why the sampling theorem says that the sampling frequency must be greater than equal to twice of the fm. No doubt it is true that the perfect sampling is always obtained only when you have this relationship, but to avoid any kind of issue related to the sampling and reconstruction, it is always preferred to have the sampling frequency greater than twice of the maximum frequency component. So we try to sample the signal at high rate, but the sampling of the signal at high rate will again can cause some problem, some issue with the system. So we cannot have the excessively fast sampling. That means we cannot have uh, the samples wherein the time period between two samples is zero. We cannot have an infinite frequency there, right? Because ultimately we are using certain algorithms to process the sample data, and generally in control systems we make use of the recursive control algorithms. So these recursive control algorithms would be hard to implement if we are using the sampling frequency at infinite rate. Now let us come to the second effect, which cause an issue or problem in implementing the digital control, and this is known as quantization. So once you have sampled the data, you have an analog quantity with you. You have sampled this particular data. So when you sample this data, you do not get the digital output. So you are getting some sampled value here, but this sampled value will be continuous in amplitude. That means whatever value you have here will be obtained as the magnitude of each sample, like this. So that means if you have sampled a data at 0, k is equal to 0, for example here. So if the value of this amplitude is 1.25, so the value of this first sample will be 1.25. Similarly, the value here will be, let us say, 1, this value is, let us say, 1.3. This value is, let us say, 1.75. This value is, let us say, 1.65. Something like this. So that means you may have the fractional values. You may have the uh, a natural number or a whole number as the amplitude, but you most of the time you may find the fractional value, right? So So here you have lost the information. So you need to round off these values. Okay. So what we do is we map this value to some 2.0. We round off it. We have 1.25. So what we do, we try to reduce it. So we'll make it 1.0. We have 3.21. So we'll make it 3.0. We have 3.89. So we make it as 4.0. So what we are doing, we are rounding off the fractional value. So this rounding of some fractional value to get, because when you will convert this into digital, so the digital values are easy to obtain for some natural numbers instead of fractional values. So for fractional values, we have a large digital sequence. So for a complete whole number or natural number, we have a small digital representation. For example, if our D A to D converter is of 2 bits. So 2 bits means 2 to the power 4, that means 4 values. Four values means 0, 0, 0, 1, 1, 0, 1, 1. So so this 0, 0 belongs to 0, this 0, 1 belongs to 1, this 1, 0 belongs to 2, and this belongs to 3, right? So if you have a 3 here, okay, so the 3 has digital equivalent as 1, 1 for 2 bit ADC. If the ADC is 3 bit, so the resolution is 2 raised to the power 3, that is 8 values. So in that case, we have 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on, and 1, 1, 1. So this is 0, 1, 2, and so on, and eighth value. So that means if the bits are increasing, the resolution is increasing, and more the resolution is, more will be the samples, right? But quantization is a process in which we are rounding off the value. So when we round off the value, even then also we lost certain information. So first we have lost the information at sampling level, then at quantization level. So we can see the quantization from this particular diagram here. Okay, so as you can see very closely that these values are being rounded off, like here. Okay, so this you can see. So the values are being rounded off. You can see it again, once again. So you have, this is rounded off, and rounded off, and then rounded off. Okay, so the reason for this is to get the uh, perfect digital representation of the analog signal. So let us see if we have some four samples. So sample values are 1.25, 2.89, 4.27, and let us say 3.12, for example, like this. So we'll round off this as 1.0, we'll round off this as 3.0, we'll round off this as 4.0, we'll round off this as 3.0, like this. So one has digital representation as 01 for 2 bit, 3 1 1, 4 for 2 bit we cannot have 4, so right. So we'll take 1 1 in this also, just to get the, and here also 1 1, right. So what I mean to say is that if we have to take the digital representation of 1.25, so in this we need to we will be having a large or long digital sequence, right. So here you can see in this particular diagram, you have an analog signal, you have its digital representation, and you have the reconstructed signal, analog signal, analog, digital, and analog, right. So this is a real time example. Here you are speaking something on microphone, it is being converted into digital signal going to some digital system. We are using A to D converter, then digital system is generating some digital signal as output. We are using D to A converter, that is digital to analog converter, and speaker is saying the same thing which a person is speaking. Okay, speaker is not giving you ones and zeros, it is giving the same thing as an output which the person is, which the speaker is speaking, right. So the conversion of signal from analog to digital form and vice versa is performed by the electronic devices A to D indeed. So this is what we have mentioned many times, and they must have some finite resolution. So the resolution is generally 2 raised to the power n minus 1, right. Then for any n bit resolution, for any n bit there are 2 n quantization levels. Okay, so if uh, we have the 2 bits, we have 4 quantization level. If we have like this, we have these many quantization level, that means these many values we can round off for the given sample data. So the analog signal is basically converted or quantized based on the resolution of the A to D converter, and to get the digital form of the analog signal, right. Now when we convert, so we lost the information, so this is one thing. Okay, so we lost the information, so we are losing the information when we are converting the analog signal into digital. We are actually losing the information, and our ultimate duty is to get the same signal in the reconstruction form. As you can see in this particular diagram, this signal is not exact as this one, but it is a staircase type, but it is representing to some extent as the same signal which is at the input, right. So this is a drawback basically. So sampling and quantization are inevitable. We need to do sampling as well as quantization for converting any analog signal into digital signal, but these quantization and sampling processes have certain issues, so we need to address those issues. We need to use the A to D or D to A converters of high resolution, so that we can have maximum number of samples. And when we have maximum number of samples, the information lost is minimum, and the lost information, because the information lost is minimum, so it is quite easy for us to reconstruct the exact signal from the sample data at the output. So this was all about today's class. Thank you so much.